Okay, we're going to do discussion 1-3, significant figures, percent error, and accuracy versus precision. Alright, so let's talk about significant figures. Here we have a beaker. And the beaker has markings only every 100 milliliters. Right, so the rule when we're taking measurements in a lab, we're going to record all the digits we know for certain from the markings, and we're going to get to make one estimated digit after that. So when we examine this beaker, I can see only one thing. The only thing I know for certain is that the volume is somewhere between 900 and 1,000 milliliters, so it's going to be 900 and something. Since I've recorded all the digits I know for certain, I get to make my estimate now. Now it looks to me that the volume level is just about halfway between 900 and 1,000, so I'm going to go ahead and call it 950. Now, because this is not a very precise device, I do not have the ability to say that it's 951 or 953. I can only say that it's 950 if I'm following these rules. So the 0 at the end of the number 950 is not considered a significant figure. It's just a placeholder telling us that the number is 950. As such, that 0 is not considered a significant figure. So the goal for you guys is going to be to look at a number and count the number of significant figures that the number contains. And there's some rules that we're going to follow to do that. The first rule is that non-zero numbers will always be considered significant. That means if the number is 1, 2, 3, 4, 5, 6, 7, 8, or 9, it counts as significant. So let's look at this first example. There's 5 numbers, 1, 2, 3, 4, 5. All of them are non-zero, so they all count as significant. So the grand total in this number will be 5 significant figures. Pause the video and count the number of significant figures in the next number. Alright, again, there is 6 numbers in this number. All of them are non-zero, so they all count as significant, so the grand total will be 6 significant figures. Now, since all non-zeros are always significant, the only number that can be insignificant is 0. So we're going to have to talk about some rules with zeros. Any zeros that are in between non-zero numbers will always be considered significant. You have to remember, when we're measuring on lab equipment, sometimes we're going to actually measure the number 0. Sometimes the measurement will actually be 800.28. So whenever we see zeros in the middle of non-zeros, if there's non-zeros at the end of the number, you know that all the zeros in the middle were actually measured zeros, so they count as significant. So in this number, there's 5 numbers, 3 of them are non-zeros, and 2 of them are zeros in between non-zeros. So of those 5 numbers, all are significant, so there are 5 significant figures. Again, pause the video and see if you can count how many significant figures are in 60.5. Alright, again, this 0 appears in between non-zeros, so that 0 will count as significant, so there are 3, that should say 3 significant figures in this number. Sorry, I hate to edit a video on the fly, but sometimes you gotta do what you gotta do. Okay, trailing zeros, in other words, zeros that are at the end of a number, will be significant if there's a decimal point in the number. If there's no decimal point in the number, then the zeros will be considered insignificant. We have to think about why. Now, 0 is not really a number. It just means none. So technically, there's an infinite number of zeros at the end of every single number we ever look at. If you look at 7, you could write it as 7.0, and that would still be 7. You could write it as 7.00, and that would still be 0. So if we are taking the trouble to put a decimal point in this number and recording those zeros, we are saying that those are actually measured zeros. So again, if there's a decimal point in the number, zeros at the end are significant, and if there's no decimal point, then they're not. So in 45.120, all the non-zeros are significant, and there's a 0 at the end of the number. Since there's a decimal point in that 0 will count as significant, and so there's 5 significant figures in that number. In 6.7100, there are 3 non-zeros and 2 zeros at the end. Since there's a decimal point in the number, they count as significant, and there will be 5 significant figures in that number. take a moment and pause the video and see if you can count the number of significant figures in the next two examples. Alright, so in 50, now we typically don't see numbers written this way, but there is a decimal point in the number. That decimal point is put there specifically to show that that 0 counts as significant. Since there's a decimal point, there will be 2 total significant figures in that number. In 189,000, we see 3 non-zeros and 3 zeros at the end. Since there's no decimal point, those zeros must just be placeholders and not actually measured numbers, so there's only 3 significant figures in this number. The final rule concerning zeros is leading zeros. That means zeros that come before a non-zero digit. So zeros in front of a number, like these zeros, and these zeros, and these zeros. Those zeros never count as significant, ever. So when we look at this number, there's 3 zeros. Those are zeros in front of the number, zeros to the left, so they don't count as significant, but the 1, 6, and 3 do. So there's 3 significant figures in that number. Okay, little preview. In this number, we have zeros all over the place. I've got some zeros to the left, and I got a 0 at the end. The zeros to the left, because zeros to the left are never significant, are not significant. But there's a 0 at the end. Since there's a decimal point in the number, it counts as significant, and so that number contains 3 significant figures. In the final example, all the zeros are to the left, and we have 2 non-zeros, so that number will only have 2 significant figures. So on this slide, we have a whole series of numbers. And what I want you to do is pause the video and see if you can work out how many significant figures are in each number. On the next slide, I have the answers. So if you, when you fill them in, check your answers. If you're incorrect in any of them, go back to the previous slides and review the rules. So there they are. Okay, moving on. We also have to take account of significant figures when we're doing math with numbers that we measure in a lab. And there's 2 different sets of rules, one for adding and subtracting, and one for multiplying and dividing. When we're adding and subtracting, an answer can only have as many decimal places as the fewest number of decimal places in the numbers you're adding or subtracting together. Well, what does that mean? Whenever you're adding or subtracting numbers, you have to look at both of the numbers you're adding together and count the number of decimal places. Whichever number has a smaller number of decimal places, that's how many decimal places we'll round our answer to. So let's look at the first example, 1.01 plus 1.313. When I add those together in my calculator, it's going to tell me that the answer is 2.323. Now I have to look at both of the numbers I added together. 1.01 has 2 decimal places, and 1.313 has 3 decimal places, so we have to have 2 decimal places in our answer because 2 is a smaller number than 3. So when I round this, I'm going to round it to 2 decimal places. Since that number is less than 5, that 2 is going to stay as it is, and we'll round it to 2.32. In the next example, when we put this addition problem into our calculator, it's going to tell us that the answer is 4.67258. Now I have to examine the number of decimal places in each number. This number has 1, 2, 3, 4, 5 decimal places, and 1.1 only has 1. That means we're going to round this number so that it has 1 decimal place. Now, to do this, I have to look at this 7. Since this 7 is greater than 5, that 6, is going to round up to a 7. So the rounded answer will be 4.7. Take a moment and pause the video and work out the last example all on your own. Okay, so when we do the math, the calculator is going to tell us the answer is 54.004. In 51, there are 0 decimal places, and 3.004, there's 3. So we're going to have to round our answer to 0 decimal places, so this number will become 54. All right, now those are the rules for adding and subtracting. The rules for multiplication and division are a little bit different. So when we're multiplying and dividing, our answer can only have as many significant figures as the fewest number of significant figures in the numbers that we're multiplying or dividing together. In other words, when we are multiplying and dividing, we have to look at each number we're multiplying and dividing together and count the number of significant figures in those numbers. Whichever number has a smaller number of significant figures, that's how many will be in our answer. So 4.26 divided by 3.1 is, in my calculator, 1.374193548. So now I examine my numbers. 4.26 contains 3 significant figures, and 3.1 contains 2. That means I have to round my answer to 2 significant figures. So I'm only going to want to keep the first 2 numbers in this big number. Again, since that number in the hundredths place is greater than 5, we're going to round that 3 up to a 4, and the rounded answer will be 1.4. In the next example, we're going to take 12 and multiply it by 3.725. My calculator tells me that's 44.7. Since there's only 2 significant figures in the number 12, we have to round this to 2 significant figures, so it will round up to 45. Take a moment and pause the video, see if you can work out this next example, put it in your calculator, write the calculator answer here, and then round to the correct number of significant figures. Alright, so there's what it looks like when I put it in my calculator. Now I have to look at my starting numbers. I took 27.85, that has 4 significant figures, and divided by 3.1212, which has 5. Since 4 is a smaller number than 5, I have to round this to 4 significant figures. That means I'm going to keep the first 4 numbers in the calculator answer. And I have to round this 2 up to a 3 because I have that 8 there. So this will round to 8.923. Alright, so with this topic, practice makes perfect, so if it didn't make much sense to you what I just did, go back and keep practicing until you understand. Alright, so let's look at an example of how this would work with a mean. It says find the mean of the following data and report your answer to the appropriate number of significant figures. Well, to get a mean, I'm going to take those 4 numbers and add them together and then divide by the total number of numbers, so I'm going to divide by 4. So when I do the addition, I have to follow the rules of adding and subtracting. So when I add the numbers together, I have to consider how many decimal places are in each one. The smallest number of decimal places in all 4 of the numbers is 1, so when I get my answer on my calculator at 7.31, I'm going to round that to 7.3. Now I have to divide 7.3 by 4, and when we're dividing, we have to count the number of significant figures, and whichever number has the fewest, that's how many will be in our answer. But it's important to note that significant figures only apply to data that we measure in the lab. When we're taking a mean, we're dividing by 4, but we're dividing by exactly 4. So the 4 does not factor into our calculation. So when we get 1.8275 as the average on our calculator, we have to round it to 2 significant figures to match 7.3. So we'll round to 1.8. Here's an example calculating density. Take a moment and pause the video, see if you can calculate the density, and report your answer to the correct number of significant figures. Alright, so density is mass divided by volume. 10.51 grams is a mass, and 2.1 milliliters is a volume. So we'll divide the mass by the volume, and when we put it in our calculator, we get 5.005 grams per milliliter. Since I divided, I have to count the total number of significant figures in each number. In 10.51 there's 4, and in 2.1 there's 2. That means I have to round my number to 2 significant figures, so 5.005 will round to 5.0 grams per milliliter. Now, when you do math problems on quizzes and tests in my class, I'm not going to make you report your answers to the correct number of significant figures. It's helpful for me if you do, but I'm not going to take points off if you don't. But I will ask you questions concerning significant figures using multiple choice. So here's the same problem that we just did, but in multiple choice form. Now, if you look at all the possible answer choices, they're all some variation of 5. Right? If you put this into your calculator, you're going to get 5.005, and you're probably going to be tempted to just click 5.005 as your answer. But since there's 2 significant figures in 2.1, the true answer would be 5.0. Alright, accuracy and precision. A lot of kids think these are the same thing, but they are totally not. So accuracy is a measure of how close your data is to the intended target. So think about a dartboard. If you're throwing darts at the dartboard and you're aiming for the bullseye, if all of your darts are clustered around the bullseye, you would say that those darts are accurate. They're close to what you were aiming for. Now, precision is a little bit different. Precision just refers to the consistency of your measurements. So let's say you're throwing at the same dartboard and you're aiming at the bullseye. None of the darts are near the bullseye, but they're all clustered in the same part of the dartboard. Now, because they're consistent with each other, we would say that those dart throws are precise, but they're not accurate because they're not close to the bullseye. So it's possible to be precise without being accurate. All right, finally, percent error. Well, in general, a percentage is part over the whole times 100. So if I wanted to calculate the percentage of female students in the room, I would need the part, which would be the number of female students, divided by the whole, which is the total number of students in the room. So all percentages are the same thing, but we use percentages for specific things. With percent error, we're seeing how far off the mark we actually were. The formula for calculating percent error looks like this. It's the absolute value of the theoretical amount minus the experimental amount divided by the theoretical amount times 100. Now, what do the theoretical and experimental mean? Well, the theoretical amount is the amount that you expect to get. It is the actual value. If you did math to calculate the density of that object, the math will tell you what the density should be. The experimental amount is the amount that we actually measure in the lab. And it's called the experimental amount because it's determined experimentally while we're performing an experiment. So essentially, percent error is just the amount that you were off divided by the amount that you should have had. So let's look at a sample. It says the mass of a baseball was measured to be 65.36 grams. The known mass of the baseball is 67.96. So what's the percent error? So the key here is to determine what is theoretical and what is experimental. If you look at this equation, since it's an absolute value in the numerator, you can flip-flop those numbers and you're still going to come out with the same answer. But you have to put the theoretical amount in the denominator to get the correct answer. So when I read this, it says the mass of a baseball was measured to be 65.36 and the known mass is 67.96. The context of the problem tells me that the theoretical amount is the known amount and the experimental amount is the measured amount. So when we plug those numbers into the formula, we calculate the percent error as 3.83%. The most common error is putting the wrong number in the denominator. So read the problem several times to make sure you get the context and figure out which is experimental and which is theoretical. And here's an example with accuracy and precision. It says the following is a result of repeated trials to measure the specific heat of water. The actual value is 4.18. So here's our data. And it says comment on the accuracy and precision of these data. So is it accurate? Is it precise? And why? So when I look at these values, they're not really anywhere near 4.18. So I'm going to go ahead and say they are not accurate. Now, accuracy is, a result is considered accurate generally when it's within 5% of the target, plus or minus. Now, that's good to know for this type of data because 5.6 is a lot more than 5% away from 4.18. But I promise you, when you see questions on quizzes and tests, it won't be nearly this ambiguous. Now, when I look at these data, because all the values are very close together, there's only a spread of 0.04 or 4/100ths of a degree. So I would say that they are precise because they're consistent. And that is the end of discussion 1.3 and the end of unit 1. Please, 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 please review these videos. Go back and redo the homework assignments. They're all on Blackboard. Make sure you study for your test, and best of luck to all of you.